Thank you, and thank you for the invitation here. It's a very nice meeting. We have already seen in this room that the complex Monge-Ampere equation, which you can write in a domain in Cn like this, where beta is ddc of. So this is just a Euclidean form in Cn. And we require that U is plurisubharmonic in some domain omega where we consider the equation. Or if we consider a Kähler manifold X, in this talk it will be a compact manifold. Then the equation has a slightly different form. We add ddcu to the Kähler form. And again, we require that this form is non-negative. So we have seen that this equation is related to the problem of finding the Kähler metric with prescribed Ricci curvature, right? And in the smooth case, it was solved by Yau. Nowadays, it's usually called Calabi-Yau theorem. But now the methods which I will try to describe are useful when we consider degenerate equation, in the sense that here f can be only non-negative. In the case of Yau theorem, we need strictly positive f. And we also consider f which is not necessarily smooth. Usually in this talk, I will only assume that f is in some space Lp. With respect to the volume form, and p is bigger than 1. Then under such assumptions, we will obtain solutions which are just continuous. But they are also geometrically meaningful in when we consider metrics with some singularities, like limits of Kähler-Ricci flow, or generalized Kähler-Einstein with singularities, or when we consider, for instance, degenerations of Calabi-Yau manifolds, like in the previous talk. Then in all these cases, you can have, you may encounter such an equation which does not satisfy all the assumptions of the Yau theorem. Okay, so let me start with this pluripotential theory. Well, the basic notions are the notion of positive form and positive current. So for the time being, I will work in a domain in Cn, open set in Cn. And here we consider differential forms, PQ differential form, so the form which has the following representation. Those are multi-indices. I will write them down. So So J is a multi-index J1 up to Jp, and K is K1 up to Kq. And those are increasing multi-indices, so Js is smaller than Js plus 1, and the same for K. So here we sum up over increasing indices, which is marked by this prime here. So this is a general form. We call such a form, this is the length of the index. We have P indices, and here we have Q. So this is PQ form. Now we define a simple positive form. So omega is called simple positive form if it can be represented. It can be written as I to the power p. So this is square root of -1, omega 1, which omega 1 bar, and the same type of forms up to p, where omega, say s, is 1,0 form.
So this is a monomial form. This is a monomial form, right?
This is simple positive, yeah. This is what I call simple positive. Sometimes you... so in particular, this is PP form. And this is needed, simple positive forms are needed to define positive forms. Now, omega is positive, and we denote it like this. If omega is PP form, and if you wedge omega with alpha, which is simple positive, n minus p, then you get something which is positive. Yeah, but I will consider only those weakly positive, so there is no need to introduce one more word, right? So this is for any alpha n minus p simple positive form. Okay? And f here we require to be non-negative. And I should have told this before. So we call omega real if omega is equal to omega bar. Real form. So in particular, simple positive are real and positive are real. All right. Equivalently, positive forms can be defined by requiring that PP form restricted to any analytic submanifold of dimension p gives you a positive density. For 1-1 forms, we have a easy characterization of 1-1 positive forms. Namely, if we write omega to be I as sum of omega jk dzj dzk bar, then the matrix of coefficients must be positive definite. So we can write bar here or not, depends. So 1-1 form omega is positive if and only if this holds. So it's positive if and only if this matrix is positive definite. Also, the theorem which is often used, say proposition, we can prove that if omega is PP positive form, and alpha is 1-1 positive, then the wedge product of omega and alpha is positive. This is no longer true if we take here PP forms for P bigger than 1. There are counterexamples for this. So 1-1 positive forms are clearly related to plurisuperharmonic functions. Because if U is C2 function, then U is PSH if and only if DDC U, which is the same as I d bar delta delta bar U, is positive, right? Here, C2. So, well, we can drop C2, so we can take U, which is only upper semi-continuous. Then U is PSH if and only if the Hessian matrix is positive definite in the sense of distributions. Now here you can take the wedge product, DDCU to the power n. N is the dimension in which we live. This is a dimensional constant times the determinant of the complex Hessian. So this is the Monge-Ampere operator. And of course, for smooth functions, it is well defined. If we try to do this for any plurisuperharmonic function, there is a big problem because we cannot multiply distributions. So to define this object for less regular functions is difficult without new methods and new notions. And the right notion which comes in here is the notion of current. Okay. So upper semi-continuous. Upper semi-continuous. Okay, so let me denote. So let's denote by C infinity PQ. Smooth forms, so with coefficients in which are C infinity, PQ forms in omega. We take the subset of smooth but compactly supported forms and denote it by D PQ. Smooth, compactly supported. And let us take the dual. So let us consider the D prime of PQ, the set of continuous linear functionals on this space. And this space, so the elements of this space are called currents of by degree n minus p, n minus q. So this space is equal to currents of by degree n minus p, n minus q.
What topology do you put on the
Hmm?
What topology do you put on space?
Well, just C infinity topology for coefficients. You have a finite number of coefficients and C infinity topology. Okay, and one can prove. Oh, I didn't tell this because I will not prove most of the things here because of the lack of time. But in these notes which were distributed, all the proofs are available. So in particular, one can prove there is too. So any current of say by degree n minus p n minus q, t a current it can be represented as a representation again using this multi-index notation. So now J is n minus p and k is n minus q. Any such current has this representation where T, J, K are distributions. So we may say that currents are differential forms with distribution coefficients. Now, as for forms, we can define the notion of positive currents. So PP current T is positive, which we denote by this, if and only if we wedge, the action of T on the form alpha, which is simple positive n minus p, gives you something which is non-negative. So for any alpha n minus p, n minus p, simple positive forms. So this is consistent with the definition for forms, right? We can wedge also currents with smooth forms. So if T is a current and omega is a form, then we can define the new current, T wedge omega, which acts on a form phi, which is smooth compactly supported of the right by degree. But this is now smooth compactly supported, so this is well defined because T is a current. And again, as for forms, we have the statement that if T is a positive current, and omega is a 1-1 form, then T wedge omega is again positive. We can also differentiate currents. Take D be just any first order operator, differential operator. Define, and T is a current. define dt of acting on, again, on phi to be minus t acting on the differential of d, capital D of phi. And this is consistent with integration by parts formula. So you get the same thing as for forms. Okay, so of course, smooth forms are currents, but there are also non-trivial examples of currents. Non-trivial in the sense that they are not smooth. And one of the basic examples is a current associated to an analytic set. So let A be, just for simplicity, zero set of an analytic function f, holomorphic. So now this is a codimension 1. We can define a current T which acts on phi by integrating the form 5, so it should be n minus 1 form over the set A. This is quite easy for if A is smooth, but if A has singularities, this is also well defined. Then you integrate over the regular part of A. This is the result of Pierre-Lalonde, that it is still a positive closed current. T is positive.
This is exercise or example?
Example. You can do it as exercise.
But T is
No, it's for Lalonde. Yeah.
supposed to have compact support.
Yes, yes. So
Outside of singularities.
no. So this is the theorem of Lalonde, that if you integrate on the on regular points, you still get a closed current. That's the point. This is because the codimension is big enough.
So it's not even it's a theorem.
This is the theorem, yeah. It was proven in 50s. Okay, and one more thing we need is norm over current. So given a compact set in our omega, and given a current T in omega, we shall define a current of course, and we will consider only currents with measure coefficients. So with measure coefficients. In general, they are distributions, but now we.
What is different?
Well, the measure acts on continuous functions. Distributions act on smooth functions.
So derivative of a measure is not a measure, it is a distribution.
And then I didn't tell this, but if T is positive, then it has measure coefficients. Okay, so now we consider only.
You can extend the distribution.
Yes, exactly. Yes, you can extend the action of the distribution to continuous functions in a unique way. Hmm?
Just constructing living simpler measure.
Well, the proof is quite easy, but it requires some notions which I have not defined. So, okay, so we define the norm of T over the set E to be, say, the sum over all coefficients of Tjk. So now this denotes the total variation of the measure over the set E. But this definition itself is not very useful. What you usually use in case of positive currents is the following estimate, namely, if T is PP, positive current, then there exists a constant which depends on the dimension, such that this norm here is bounded by a constant, as I said, dimensional constant, times the integral over the set E of T wedged with the scalar or Euclidean form to the power n minus p. So this is a positive measure then. And we will use this estimate several times. Here, yeah, this is over increasing multi-indices. This is sum over increasing multi-indices.
Is that known? Sorry, I wrote this part. The part of it. No. Yeah, and the end of this part. What is this normal?
Total variation of the measure.
Okay.
I mean, each of those. Okay, and now we will see how it works for, at least for bounded plurisubharmonic functions, because then we can define the wedge product of DDCUs. And this is based on the following proposition of Bedford and Taylor. The proof is in a few lines, so I will give it. So we have a plurisubharmonic bounded function in omega, and we have a positive closed current T. Then the proposition says that if you multiply U by T, it is still a well-defined current. And moreover, if you differentiate this current by D and DC and D, then you again get a current which is positive and closed. And this is by definition, so you define DDCU wedge T by this. Is positive and closed. So before I prove it, let's see why it is useful. Now take the collection of plurisubharmonic functions which are bounded. Bounded PSH. Then using this as times, you can define DDCU1 wedge DDCU2 wedge DDCUS. And you get that it is closed, well-defined current. At this moment, we cannot say if it is symmetric in this function with respect to those functions, but it is. It comes from the theorem I will give later. So let us prove this fact. Okay, since T is positive and closed, T has measure coefficients. we have a function which is PSH and bounded. By the standard procedure using a smoothing kernel, we can find UJs which are PSH and smooth, such that this sequence decreases to U, and we work locally. So here we are in omega. We fix a point in omega, and we take a relatively compact open set in omega, and we do everything in this set. So in this set we can find such a sequence. Then by the Lebesgue domination convergence theorem, we know that Uj wedge T converges to U wedge T as measures, in the sense of measures. Now we can differentiate using the definition of using this definition. So we can differentiate this, and this will again weakly converge to now. Since functions Uj are smooth, then this can be written, and T is closed, because D and DC, it's easy to see that if T is closed, then DC of T is also 0. So if you act with D, DC and D on T, you get 0. So we are left with this. And those currents are, by the statement here, those currents are positive and closed. So we have proved that since they converge to this, this is a limit of currents which are positive and closed, so it is also positive and closed. Okay. How much time do I have? 18 minutes. Okay. Okay. So we have proved that we can wedge currents associated to bounded pluripotential harmonic functions. But we can do also the same thing for currents of this type. Now, still, U is PSH and bounded. In fact, locally bounded. Everywhere here, locally bounded is enough. We can also define this for T closed positive. Which is just 1/2 of, say, d dcu square, wedge T minus u d dcu T. I will explain. We can add, u is bounded, we can add a constant so that u is non-negative. And then if u is non-negative and PSH, then u square is also PSH. Then this is well defined by the previous proposition, and this is also well defined. So the left-hand side is well defined. Now taking two different functions, again in this category, we can also define the U wedge DC V wedge T by polarization and using this. Since we often integrate by parts, we also need this sort of currents. So in particular, in particular, we can define the Monge-Ampere operator for U, which is only PSH and locally bounded. Then DDC U to the power n is well defined. In case of Keller manifolds, we have seen that, we have heard that omega, the Keller form omega is locally given by DDC of some potential function V. So then if we consider omega plus DDC U for U, which is locally bounded and such that U plus V is PSH, then this is also well defined.
I'm missing something. Didn't you forget here also DDC of the product U, which U2, which U?
Where?
The top formula there.
Yeah, we only have U.
The fourth term, like DDC of U, which V.
Okay, let's differentiate this, right? DDC U square wedge T.
Yeah.
T is closed, so we have 2 times D of U DCU wedge T, right? And then we have D acting on U, so this is this. And D acting on DCU, then this is this, right?
But you somehow assume that DDC of U squared T is...
No, it's here.
Oh, sorry.
Okay, now I will present some basic tools in this theory. We have to use Stokes' theorem a lot of times, but then we need it for currents, the version for currents. So assume the boundary of omega is C1 smooth. T is a current defined in the neighborhood of the closure of omega. But here we assume more, namely we assume that in fact T is smooth in the neighborhood of the boundary of omega. Or C1 smooth. Of course, this is 2n minus 1 current. So then we have this 2n minus 1 current. This can be, from the classical version, you get this by approximation of the current T by smooth forms.
Right. So it is easy to ask it a bit less smooth in parts, C1 smooth by parts, because technically it's more convenient.
Yeah. Yes, okay, piecewise smooth boundary, you mean? Of course, yeah, sure. Yes. And also one of the basic tools is the Chern-Levine-Nirenberg inequality. Which has different versions. Sharper version was proven by Demailly, and I will give this one. Namely, we have a collection of PSH and bounded functions in omega. What do we have? And we have a compact subset K. then there exists a constant C, which depends on k and omega, such that if we take the norm of the current ddc u1 wedge up to ddc, say uk, over this, this is small k, over the set E, then this is bounded by this constant, over the set k, by this constant, okay, k, put S not to be misguided by this. And here we take L1 norm of one of the functions, it doesn't matter which one, say first one, L1 norm in omega, and then subnorms of the remaining ones.
Can you please say it again?
Okay. So we have functions which are bounded and PSH in omega. We have a compact subset of omega. And now we know that it is well-defined current, ddc u1 up to ddc us. The norm of this current,
This one.
the norm defined here, yes, over the set k, is bounded by a constant which depends on k, but not on the functions. And here we have L1 norm of omega and L infinity norms of other ones. We can single out one function and take L1 norm. This is needed for one of the applications, so we need this stronger version. And L infinity, the original Chen-Li van Nierenberg, we had only L infinity norms everywhere. But so maybe just to give you an idea, I will prove one step in the proof, which is, well, maybe essential step. Step of proof. Fix open set which is between k and omega, say u, relatively compact in omega. Take a test function chi, which is supported in U, which is equal 1 on k. That's it. And we fix t, which is closed and positive. This is one part of this, but without 1. T is closed positive. And we need to bound the norm of ddc u1 wedge t on k. Using this, you can replace the norm by this expression. Wedge beta to appropriate power so that the whole thing has nn, is nn currents, so power k. But now, since k is equal to 1 on k, we can put k here. Now we integrate by parts. This is a test function. Okay, so this is less or equal the same integral over omega. We integrate by parts then, and we get, okay, maybe in u. U not ddc chi wedge t wedge b to the power k. And now this is a smooth form. So if we wedge those forms, then this is a constant which depends only on chi, but this depends only on this choice of sets. So this is a constant times beta to the power k plus 1. Which means that everything here is bounded by a constant times the norm of t times L1 norm of u naught. We can start with u naught, which is negative. So this is bounded by constant L1 norm of this guy, and the norm of theta of t times beta over u. This is one step. You have to iterate this, not in a easy way, very easy way, but not very difficult. Okay, now next important notion is the notion of capacity.
You mean this is essential part of the proof?
Yeah, well, yes, in a way, but the rest is not. I mean, this iteration is not trivial. You have to cook up a collection of functions, and so it's not quite trivial, but you will find it in these notes. So our theory is called pluripotential, so we need capacities. And the most important one is it was introduced by Bedford and Taylor. I will define this in two cases, so omega in Cn, and also for compact Keller case. So let's take the first one. Take the set E. You can take compact or Borel, more general. So first you define by compact sets, and then using classical tricks in potential theory, you can extend this definition to Borel sets. So the capacity of the set E with respect to set omega is the supremum over the integrals over set E of ddcu to the power n. So we take the Monge-Ampere operator acting on u, and we take the supremum over u, which are PSH in omega, and with values between, say, -1 and 0. And you can prove this, and this was proven by Bedford and Taylor, that this they are bounded. Bounded, yeah. So this is this supremum is attained by one particular function at least. So this is ddcu. I will explain everything. Star denotes the upper semi-continuous regularization. So this is the smallest upper semi-continuous function, which is bigger or equal than ue, and ue is the extremal function of the set E. So this is the supremum over all PSH functions in omega, such that u is less or equal 0 in omega, and u is less or equal -1 on E. So in fact, this supremum is attained by one function. And in the case of Keller manifolds, asterisk is, no, this supremum needs asterisk to be plurisubharmonic. Without asterisk, it's not necessarily upper semi-continuous. Okay, take this function. If you define it like this,
But you should denote this function with asterisk.
no, the supremum is without. And you add asterisk, and then if you add this, it becomes plurisuperharmonic function. It becomes upper semi-continuous function, and this way it becomes.
Supremum of pure subharmonic is pure subharmonic. Supremum of pure subharmonic.
No, in general not.
So maximum isn't.
A maximum of finite collection, yes. But here we have infinite set. You can use Schocker lemma, and so we can prove that this supremum is really a supremum over a countable set, but still you need a regularization. How much time? Yeah, it's over. So I will just add the definition.
Anyway, the next break is 40 minutes. Except that we will.
No. I mean, for me it doesn't matter, but just for completeness, let's put the same definition in the Keller case. So now K is a compact subset of X, which is compact and Keller. And we define the capacity of K. Now we don't have the other set, so this is the supremum over. Where U is, I will put a name on this omega PSH with values between, let's say, -1 and 0. Omega PSH means that U is upper semi-continuous and satisfies omega plus BDCU bigger or equal to 0. Here we consider bounded functions, so it's okay. You can define this. Okay, thank you.
Questions? So what does asterisk mean? Sorry.
Upper semi-continuous regularization, so you have a function, f, which is not continuous. And then you consider all upper semi-continuous functions which are bigger or equal f, and take the infimum over this family. In this way you define f asterisk, f star.
It remains, if you start with something pure subharmonic, this guy is also pure subharmonic?
Yes, yeah, exactly. I mean, without star not, but with star it is.